Okay, sorry for the technical issue. So today, in this session, Jaylen and I were talking about the OAI Cooling Workstream progress update. And I'll go through some first few sections, and Jaylen will cover the most of the parts, actually. So what does the OAI Cooling Workstream do? Our goal is to really to establish a specification, framework, standardization, and best practice of all the advanced cooling solutions for OAI systems and OEM products from multi-level to system level. When we talk about rack level, that's a different thing, yeah. In year 2021, we are focusing on analysis and prototype practice of the single-phase liquid cooling solutions to support OEM at a 1 kilowatt level, while in year 2022, we are focusing on OEM 2.0 and UBB 2.0 thermal spec and the guidance development. We also have immersion cooling exploration, which we are seeing a later presentation in the immersion workshop this afternoon. Looking into the OAI domain, we are facing several challenges. The foreseeable OEM power demand growth, this compact modular and system layouts with high power densities. And lastly, but not least, there's a huge variation of boundary conditions and design philosophies across different designers, suppliers, and then customers. In order to answer some of those questions, or at least building more clarity into this domain, we have made those efforts as listed. We are developing the OAI liquid cooling guidelines that's already published as a white paper in the server project wiki page. We have done the practice on the 1 kilowatt level thermal test vehicle and cold plate loop assembly. We're also performing the cooling analysis for OEM 2.0 and UBB 2.0. A glimpse of the user requirements. The user requirements could vary a lot across different regions, different customers, for different even products. Even Meta has many different data center types. But if you try to simplify the boundary conditions and group them in smaller variations, we have the high coolant temperature group, we have the medium coolant temperature group, we have a low coolant temperature group. And for the studies this group performed, we are focusing on the group 2 assumptions. Our performance data are also applicable to group 1 and group 3 by offset. If there's a need or desire to study other groups of boundary conditions, let us know. A glimpse of what's covered in the liquid cooling design guidance. It covers user requirements, what I just showed. We talk about the OEM thermal challenges at a relatively general level, but you will see a lot of scientific and engineering thinkings into that statements. There's OEM reference cold plate design. There's practice of cold plate loop in the UBB system. There's many paragraphs talking about validation and reliability. And lastly, but not leastly, there are multiple case studies contributed by a few partners in this community. And there are some good insights into the current challenge, how do they solve the current challenge, and how they are able to extend our capability into the future. Okay, next we'll hand it over to Jaylen and talk about the really details and contents.
Hello. Great. Thank you, Chen, for the introduction. And I'm Jaylen from the Wiwynn thermal team. And this picture shows our passive cold plate loop design, which is the 4x2 design as a traditional net flow work. And for the dummy board and the TDV in the system, we follow the UBB 1.0 and the OM 1.0 spec to do it. And for the 1 kilowatt cold plate and the TDV design, and we designed the cold plate based on the OM 1.0 spec. And we use the 30 by 30 foil heater to generate the heat up to the 1 kilowatt as a OM TDV. And this is a top view of our prototype systems, and the OM TDV number 1 to number 4 at upstream, and the number 5 to the number 8 are at downstreams. Our test condition is the 30 degrees C treated water, and the coolant flow rate from the 6 LPM to the 14 LPM, and the testing power for each TDV are the 1 kilowatt. And this is our practice result, and based on this result, this gives us a very good confidence that the liquid cooling solution could support the future high power cooling demand based on some given conditions. So and we could see it almost no temperature variation of downstream TDVs. It shows a good cooling distribution of the PCL design. And apart from the liquid cooling solutions, one of the focuses of our cooling workstream is to develop the UBB 2.0 thermal spec and the design guidelines. And this is the basic information of the UBB 2.0 systems. We could see we have the FPS expansion card and the FPS OAM 2.0, and they have a very high TDP. So the very high power density and the compact system layout design put a lot of restrictions of the thermal design. But although the thermal design is a challenge, but we still expect that the air cooling solution, we could push out the limitation up to above the 450 watts per OAM. And for the extremely high power TDP, and we could, liquid cooling could be a choice and based on our prior test result. So for the following pages, I'm going to share some component level and the system levels and thermal analysis. This is a reference heatsink design adapted to the 3D vapor chamber technology. It could provide a very good performance to cooling the OAM. And but we're still working on the optimizations and to reserve more the thermal margin for the OAMs. For the expansion card design, and this expansion card TDP depends on the application, and we choose the 200 watt type, which is a retirement type as our baseline starters. And it's designed for 4U form factor, and our result shows that the expansion card could have sufficient cooling at the cold aisle, but it could not have enough thermal margin at the high aisle. So we are working on the system level optimization to see how to let it to support the higher local ambient temperature. So to find out the limitation of the OAM TDP, and we performed the thermal analysis based on varying OAM TDP. And our result shows that if we could provide sufficient airflow, and we could push out the OAM TDP above the 450 watt. And under our maximum airflow rate, the fan power will be around 10%. So if we still want to push out the limitation, we need to increase the airflow. Here's some ways to increase the airflow rate. Like we could enhance the fan performance, increase the fan speed for driving the more airflow rate, but the fan power will be increased too. And we could use the more fans for the airflow driving, like the picture, and we could put the 4U UBB layer into 6U systems, and to share the fan wall with another 2U handle. And under the proper airflow distributions, we could let the UBB layer have more airflow rate for the cooling capability extensions. But all of the analysis have some dependency, like the thin material and the OAM package design and some variations. So we should take them into account. So if they still have a restriction to use the air cooling solutions and need to upgrade to the liquid cooling solutions, here is a liquid cooling solution based on the UBB 2.0 layout and the 1 kilowatt cold plate design. User could reference it and have the modifications based on their requirement, like the thermal performance or the serviceability or anything else. So this is all the update from the cooling workstreams, and although that we already have some achievement, but we still have a lot of area we cannot explore too. So we're looking forward to more participation from the community. So if you are interested to get involved, please reach out to the Chen for the cooling group and reach out to the Stone for the OAI group. Thank you.
Thank you.
Thank you.
I think we have a couple minutes for a few questions if necessary. And although I not a lot of audience here for probably the next upcoming session, but really thank you for showing up.
Thank you.